Welcome back. This is topic 5.7, the periodic table. Last semester, we didn't have quite enough time to tie in valence electrons and electron configurations to the structure and arrangement of the periodic table. So the start of this semester, we're just going to spend a few days talking about the structure of the periodic table and patterns that are arranged within it. So the first thing is we had Dmitry Mendeleev come along. He was a Russian chemist who took the elements that were known at that time, and what he did is he basically made these cards where he listed out the name of the element, its mass, and some basic properties that were known about that element. And so the one thing he did was kind of like playing the game of solitaire, where he had a column or the up and down grouped together based on similar properties. And so other people were doing that same thing that he was doing, and he saw that there was that pattern, that there was a trend by not only arranging it by increasing atomic mass, but using these properties, that there were some inconsistencies on how to keep his pattern flowing together correctly. So what Mendeleev did at that time that was very critical compared to other chemists at the time is he knew that not all the elements had been discovered. For example, one of them that he predicted that we didn't know at the time was gallium. So this blank spot here underneath aluminum is he knew for his periodic table to work that there had to be an element here that was not discovered at that time. And so that was the one thing he did that set him apart from other scientists, is he knew that not all elements were discovered and where to leave blanks for these undiscovered elements. As we progressed through time, Henry Moseley came along. He was a British chemist who changed the arrangement of the periodic table, and instead he arranged it by increasing atomic number, or protons, versus mass. Again, they didn't know about protons at the time Mendeleev was working on this periodic table. And so the one thing it helped fix is it helped keep elements with like properties grouped together in those columns. From that, we get what's called periodic law. And so this is what happens when you arrange all of the elements by increasing atomic number, that you have this pattern that repeats. So as you read through the periodic table and as you move from row to row to row, as you go from one to the next, there's a repetition and we see that pattern appear. And so the one thing that we do see is that when we arrange them by increasing atomic number, there are a few instances in which the mass goes down. So as you go from 18 protons to 19 protons, your mass actually dips. When you go back to calcium, it picks back up and starts to increase. There are a few other places in your periodic table that it does this, where mass goes down and then goes back up. So two general ways of looking at the periodic table. The first way is to look at it as these vertical columns. These vertical columns are called families or groups. And so what happens is, as you look at a family or group, you have a number of protons increasing. And if you think of it as electron configurations, we have energy level 1, 2, all the way to energy level 7. And so when you number your families or group, we leave this bottom region out, and we'll talk about this region a little bit more later on. But starting here on the left, this group in red is group or family 1, and it goes all the way to group or family 18, which we recognize as the noble gases from our configurations that we worked on last semester. And so as you go from left to right, again, you can number it. Some periodic tables use this A or B numbering system, so sometimes you'll see this numbered as 1A, 2A, and instead of numbering this as group 13, they'll identify it as 3A. They do that to distinguish what's called the main representative elements from the transition elements, which we will describe more here in a moment. When you think about a family in terms of genetics, you know that there's going to be similarities in physical appearances. And so that's why we call these families, is what happens, what ties these columns together is they end up with the same number of valence electrons. And so because of those valence electrons, that ties to chemical and physical properties. So all of these elements have one valence electron. All of these here in orange have 2, yellow has 3, all the way to the noble gases having 8, with the exception of helium having 2. And so because they have the same number of valence electrons, again, they have similar characteristics. The other way we can look at it is the side to side or row to row, which are called periods. And so every period starts with a metal, and specifically an alkali metal, and it ends at family 18, which are the noble gases. There are 7 periods to the periodic table, and so it just is, a change in the properties. When you come back to the next row, those properties start all over again, and so it's that natural progression following periodic law. So like I mentioned earlier, we have these some periodic tables that number with this A system, where it'll have 1A, 2A, 3A, all the way up to 8A. Those are the elements here in red. They are the ones that sit above. You can identify those as the S and P block of the configurations. And so we call those the representative elements because it basically represents the wide range of both chemical and physical properties of the elements in those areas. And we'll talk about that more here momentarily. The transition elements are here in green. That's the D block. So basically what it does is we have the metals here on the left side of the periodic table, and nonmetals are found here on the far right. And so we call this basically the transition metals because it's like a bridge that makes that transition from metallic characteristics to non-metallic. Sometimes we see the numbering system using the letter B, so A's follow elements that are representative elements. The B's follow those that are transition. So there are 3 ways we can classify elements. We can classify an element as being a metal, nonmetal, or metalloid. We can also determine if it's a solid, liquid, or gas at room temperature as well. So metals, general characteristics of them is that they have luster, or that they reflect light. They are great conductors of heat and electricity. They are malleable and ductile, meaning you can shape and form them, which is you can make coins in aluminum foil, and we can make copper wiring. Ductile means you can stretch it into that wiring. Of all the metals on the periodic table, they are all solids. There are no metals that are a gas at room temperature, and the only other exception is mercury is a liquid at room temperature. Otherwise, again, they are all solids. And these are found to the left of the stair-step line, and I'll show you here what I mean by that. At some point, you may want to come back to this or pause this and draw this onto your periodic table, but this orange line is what we call the stair-step line that starts and follows along boron and divides it out. So we have here in all of the blue here, this represents elements that are metals. So you can see the grand majority of the elements on the periodic table are definitely metallic in nature. And so like I mentioned, we call this transition because as you go left to right, we transition into our last 2 categories. Nonmetals tend to be either a gas at room temperature, or if they are a solid, they are brittle. So basically all the properties of a metal, nonmetals are not going to follow those traits. So if you hit a metal with a hammer, it's going to dent or shape. As where a nonmetal, if you hit it with a hammer, it's probably going to shatter and crumble into smaller pieces. For example, chlorine is a gas at room temperature, and then we have one liquid nonmetal, and that is bromine. So here's bromine. It's a rusty kind of colored liquid, but it changes to a gas right above room temperature. So we only have 2 liquids on the entire periodic table at room temperature, and again, that's bromine and mercury. Otherwise, the remaining is going to be the majority being solids, and then gases kind of being in second place. So again, like I said, everything that a metal is, essentially a metal is not going to be. So that conductivity of heat and electricity, that malleability, all of those characteristics are not observed in the nonmetals. So nonmetals are in the kind of brown on the far right. So again, these take up the second majority of the periodic table. You will notice one is out of place, and that is hydrogen. That's due to the fact that we have our groups organized by valence electrons. Hydrogen has 1 valence electron. Therefore, lithium, sodium, all the way down is also going to follow that pattern with 1 valence electron. So the last remaining group are metalloids, and sometimes they are called semi-metals. And so that basically is identifying that they are kind of a blend in characteristics. They are both metallic-like and non-metallic-like in properties. And so two elements from that group that you may have heard of is silicon and germanium. Because of their blended characteristics, they form what are called semiconductors, in that they do not conduct electricity quite as efficiently or effectively like a metal, but they do conduct much better than a non-metal. And so that characteristic is desirable when designing things like computer chips and solar cells. And so these, oftentimes, that's their claim to fame on where they get used, is in the tech industry. So those make up the minority of the periodic table, and typically the elements that touch that stair-step line are going to be considered these metalloids, with the exception of aluminum that touches the stair-step line, and polonium. Those are considered metals. All the others are metalloids. So like I said at the beginning, we have 18 groups or families on the periodic table, and some of them have distinct characteristics. So you'll see in the image, we have group or family 1. Identified in green, those are the alkali metals. Notice that hydrogen's left out. It's not considered an alkali metal, but it's with family 1 because it has one valence electron. So these are the most reactive metals of the periodic table. As you move down the family, they become progressively more reactive, and it gets to the point that they are reactive and radioactive. And it's all due to valence electrons. So it's a game of being like Goldilocks and the Three Bears and being just right. And so these metals have two options: gain or lose electrons. So it can lose one valence electron, or it can gain 7 to fill up that S&P. It is easier for it to lose one electron, and so they are desperately trying to get rid of it. And so you can see that reactivity in the beaker, that if these are exposed to moisture in the air, if it comes in contact with water, for example, it's a very violent reaction. The one thing that is interesting about these is this is what sodium, pure sodium, looks like. So this corrosion occurs due to its reactivity. So when it's freshly cut, and that's another thing that's interesting, is it's soft enough to be cut with a knife, is that it has that metallic sheen. If you give it a moment, it'll corrode and have that kind of same coating on the outside. So these are often stored underneath some type of oil to prevent them from coming in contact with, again, water. As we progress to the right, in this lime green here, we have group or family 2, which is identified as the alkaline earth metals. And so these are less reactive than group 1, but they are a reactive group. And so they have 2 valence electrons. So these will lose 2 valence electrons versus gaining 7. And so you can see here the overall images, you can see they have that metallic-like appearance. So when we jump over, so we have the transition metals here, we're going to jump here to family 13. Family 13 through 16 don't have a really fancy name like alkali metal and alkaline earth metal, and what they're named after is the element at the top of the family. So in family 13, boron is the top, so it's the boron family. Group 16, oxygen is at the top, it's the oxygen family. These ones don't have distinct characteristics quite like the first 2 groups we discussed. It's because they're a blend of those metals, nonmetals, and metalloids. And so because they have that blended-like nature, they don't have, again, those unique characteristics. So again, these are all the transition metals. So we don't identify those with distinct traits. So we have the boron, carbon, nitrogen, oxygen. So that takes us to our next family, which is group 17, the second one from the right, and these are identified as the halogens. So the alkaline metals are the most reactive metals. Of the nonmetals, the halogens are the most reactive. And so it's due to the fact of, again, that game of Goldilocks and the Three Bears. And so it has 2 options: gain 1 valence electron or lose 7. It is definitely much easier to find 1 valence electron than to find somewhere to take 7 electrons to. And so they are desperately seeking out 1 valence electron. So the alkali metals are trying to get rid of it. The halogens are trying to take it on. And so of that group, this has an opposite pattern. So the alkali metals get more reactive as you move down the family. The halogens get more reactive as you move up. That makes fluorine the most reactive element in the family. And so it can become kind of a nasty element to work with. It can eat through glass and things like that because it's a gas at room temperature. So it's not oftentimes used in much in terms of pure fluorine, because again, it is very, very reactive, and it's due to those 7 valence electrons. So the last group, this name should ring a bell, that's group 18, and so that's the noble gases. We use those with our configurations for this reason. Those had a full valence shell, meaning they had 8 valence electrons, with the exception of helium only having 2, but the one thing they both have in common is that that outer shell is full. So again, like Goldilocks and the Three Bears, this is the example where it's just right. And so because these have the number of desired valence electrons, we call them inert. And inert is just another way of saying that they are unreactive. They're not looking to gain or lose valence electrons, and so they aren't trying to form a chemical bond with other elements. So it actually took us a while to discover these elements. They occur in trace amounts in our atmosphere, and because they don't react and form compounds on their own naturally, that means it took a while to discover them. And so again, overall, they have 8 valence electrons, helium being the exception and having only 2. So families 3 through 12, you can see here it's numbered with that B system, and then up here the representative groups are named with that A system. And so we don't have specific names assigned to these elements. We just call this overall D block of the periodic table transition metals. And so a lot of times these are where our fancier metals come from. So sometimes they're called coinage metals in here. So group 11, for example, is a lot of those coinage metals of copper, silver, and gold. So this bottom part of the periodic table, if you remember, this is the F block of the periodic table. And so a lot of times, and I'll show you what this looks like here momentarily, is I get asked, why is this placed below? And it's quite simply the only reason why these two periods or rows exist on their own is to conserve space. So how we name them, lanthanide, if you take a look, this is where the element lanthanum occurs. And so we name it for the element that precedes or starts the group. And so these are sometimes called rare earth elements as well. The row below it follows the element actinium, so we call it the actinide series. And so the one thing that is interesting in this group is that they are all reactive. And then once you get past atomic number 92 or uranium, so 93 on up, they are radioactive, but they're also synthetic, meaning that these are not naturally occurring radioactive elements. These are ones that have to be formed in the lab synthetically, and we do that through particle accelerators and cyclotrons, for example. And so we created those elements to essentially complete the periodic table all the way out to element 118. So this is what the periodic table really does look like. If we had enough space and room, this is what it should look like, where we have our P block here, the D block here, and so the F block would fit here in between where the S and D is found. And so again, all we do is we cut out this region, place it below, just so their periodic table can fit onto a sheet of paper, for example, or fit more easily into some kind of resource or handout. So from here, what you guys have remaining to do for today is to color the 2 periodic tables following the instructions that are provided. If you have any questions or concerns about it, feel free to reach out to me.